a galaxy blazes across 13.4 billion light-years of space. It should not exist. When we peer at this distant system, we see it as it was less than 300 million years after the Big Bang, when the universe was only 2% of its current age. At that time, only hydrogen and helium existed, yet this tiny galaxy burns bright with oxygen, an element that demands generations of stars to form, live, and die in violent explosions. We will explore how this impossible discovery rewrites cosmic history, witness the shocking chemistry that should not be there, and reveal what this means for everything we thought we knew about the birth of galaxies. If you enjoy unraveling these cosmic mysteries with us, hit that like button and subscribe. Prepare yourself. We dive in now. Scientists found something that breaks every rule. A galaxy exists when the universe was less than 300 million years old. Picture the entire history of the cosmos, compressed into 1 year. This galaxy appeared on January 7th. Everything we understand about chemistry, star formation, and time says this should not be possible. The discovery came from a tiny point in the constellation Fornax. When astronomers aimed the James Webb Space Telescope at this region, they expected to see primitive structures. Instead, they found a system blazing with complex chemistry. The galaxy designation reads as a string of letters and numbers, but scientists simply call it the record holder. It sits 13.4 billion light-years away. Here lies the core problem. At 300 million years after the Big Bang, the universe was 2% of its current age. Imagine a human infant displaying the knowledge of a teenager. The comparison actually understates the situation. This galaxy contains oxygen, an element that demands multiple generations of stars to create. Each generation requires millions of years to form, burn, and die. The math refuses to work. Traditional models predict that galaxies at this epoch should be small, dim, and chemically simple. This one violates all three predictions. It shines brighter than expected by factors that make astrophysicists uncomfortable. Its size extends across 1,600 light-years, making it substantial rather than compact. Most shocking of all, instruments detected significant amounts of oxygen mixed throughout its structure. The element oxygen forms only inside massive stars through nuclear fusion. Those stars must then explode as supernovae to scatter their contents across space. New stars form from this enriched material, continuing the cycle. This process cannot happen quickly. Physics imposes speed limits on stellar evolution that cannot be circumvented. Research teams calculated backward from the observed oxygen levels. The galaxy must have been forming stars for potentially 100 million years before the observation. That pushes star formation back to within 200 million years of the Big Bang. The universe barely had time to cool from its initial expansion. Dense clouds of gas barely had time to collapse under gravity. Yet somehow, this system assembled itself, ignited multiple stellar generations, and created chemistry at a pace that current theory cannot explain. Two independent teams verified the findings using different instruments. The near-infrared camera captured the initial imaging. The mid-infrared instrument revealed the oxygen signature. Later, radio observations from the Atacama Large Millimeter Array in Chile confirmed the oxygen detection with extraordinary precision. The measurements align perfectly across different wavelengths and different observatories. What you see here challenges cosmology at its foundation. Time becomes the villain in this story. The universe has rules about how fast things can happen. Stars need time to form. They need time to burn their fuel. They need time to die and spread their ashes. Every step requires millions of years. This galaxy completed the entire sequence before it had the time budget to do so. Think about baking bread. Mixing the ingredients takes minutes. The dough needs hours to rise. Baking requires more time in the oven. You cannot compress these steps. the chemistry demands its duration. Stellar alchemy works the same way. Hydrogen fuses into helium over millions of years in stellar cores. Heavier elements form through sequential burning stages as the star ages. The final explosion happens only after the star exhausts all possible fuel sources. The numbers create an impossible equation. This galaxy appeared at 290 million years after the Big Bang. Oxygen appears in its spectrum in quantities matching galaxies billions of years older. The first stars needed time to collapse from primordial gas clouds. Estimates place first star formation no earlier than 100 to 200 million years post-bang. That leaves a window of perhaps 150 million years maximum. Within that window, several things must occur in sequence. First-generation stars must form from pure hydrogen and helium. These population 3 stars were likely massive, perhaps 30 to 300 times more massive than what we see today. Such giants burn hot and bright, exhausting their fuel in mere millions of years. When they explode, they disperse oxygen, carbon, and other heavy elements into surrounding gas. That enriched gas must then cool and collapse again. Second-generation stars form from this material. Some of these also burn through their fuel and explode. The cycle repeats. Each iteration adds more heavy elements to the mix. The concentration builds gradually over time. To reach the levels detected in this galaxy requires multiple cycles. Each cycle takes time measured in millions of years. Computer simulations of early universe star formation consistently show that building significant metal content takes longer than this galaxy had available. The models include factors like gas cooling rates, gravitational collapse timescales, and stellar evolution phases. Even pushing every assumption to its absolute limit, scientists cannot make the timeline work under conventional physics. Some researchers propose that early stars formed much faster than current models predict. Others suggest that supernovae dispersed their contents more efficiently in the denser early universe. A few radical theories propose that the first stars were far more massive than believed, burning and dying in accelerated timescales. None of these explanations feel fully satisfying because they require reworking fundamental assumptions about how gravity, pressure, and nuclear fusion operate. The timeline problem extends beyond this single galaxy. James Webb has found other systems at similar distances showing unexpected maturity. The pattern suggests something systematic rather than a statistical fluke. The universe apparently mastered galaxy formation far faster than our best theories predicted. How fast remains terrifyingly unclear. Go back to the beginning. Nothing existed. Then everything exploded into being. In the first seconds after the Big Bang, the universe was too hot for atoms to exist. Temperatures exceeded billions of degrees. Matter existed as a seething plasma of fundamental particles, quarks, and gluons colliding in chaos. As the universe expanded, it cooled. Within 3 minutes, protons and neutrons could bind together. The first atomic nuclei formed. This era, called Big Bang nucleosynthesis, created the cosmic inventory of light elements. Hydrogen nuclei appeared first. Simple, single protons. Some collided and stuck together, forming deuterium, heavy hydrogen with 1 proton and 1 neutron. Deuterium nuclei then fused into helium, with 2 protons and 2 neutrons locked together. The process continued briefly. Trace amounts of lithium formed. Tiny quantities of beryllium appeared and quickly decayed. Then the expansion cooled everything below fusion temperatures. Nuclear reactions stopped. The universe ended up with roughly 75% hydrogen and 25% helium by mass. Lithium contributed less than 1/10 billionth. Nothing heavier than lithium existed anywhere. This primordial soup drifted in darkness. Even though nuclei existed, complete atoms could not form yet. The universe remained too hot. Free electrons zipped around, unable to settle into orbits around nuclei. Photons, particles of light, constantly scattered off these free electrons. The cosmos was opaque, a thick fog where light could not travel far. 380,000 years passed before the universe cooled enough for electrons to bind to nuclei. Neutral atoms finally formed. Hydrogen atoms appeared, each with one electron orbiting one proton. Helium atoms formed with two electrons orbiting their two protons. This moment, called recombination, cleared the fog. Photons could finally travel freely through space. The cosmic microwave background radiation we detect today began its journey at that instant. Now the universe was transparent but dark. Atoms existed, yet no stars had ignited, no galaxies had formed. Space consisted of vast clouds of hydrogen and helium gas, slowly drifting under the gentle pull of gravity. Tiny density variations, quantum fluctuations from the Big Bang itself, created slightly denser regions. These denser patches had stronger gravity. They began pulling in more gas from surrounding space. The Dark Ages had begun. For the next 200 million years, nothing shone. No nuclear fusion occurred. The universe was cold, dark, and waiting. Gas clouds continued growing denser through gravitational attraction. Slowly, gradually, some clouds compressed enough that their centers grew hot. Pressure built, temperature climbed. Finally, in the densest regions, hydrogen nuclei began colliding with enough force to fuse together. The first stars ignited. They blazed with pure hydrogen and helium, nothing else. No carbon existed to form planets. No oxygen existed to create water. No iron existed to build cores. The universe contained only the two lightest elements. Everything heavier had to be manufactured inside stars through nuclear fusion. The periodic table was mostly empty, waiting to be filled through stellar alchemy. That pristine simplicity makes the discovered galaxy so baffling. Where did its oxygen come from? Imagine a universe with light, but nothing to see. After recombination released the cosmic microwave background, photons streamed freely through space, yet nothing existed to reflect or absorb them in interesting ways. Just endless expanses of hydrogen and helium gas, transparent and featureless. No stars, no galaxies, no structure of any kind visible to any hypothetical observer. This dark age lasted perhaps 200 million years. Some estimates push it to 400 million years. The exact duration remains uncertain because we have not yet observed the first stars directly. They lie just beyond current detection limits, tantalizingly out of reach, even for James Webb. We know they must have existed because later galaxies show their chemical fingerprints. The darkness had to end somehow. During these dark ages, gravity worked tirelessly. Invisible dark matter had already begun clustering. Its gravity pulled normal matter along. Hydrogen and helium gas flowed toward the densest concentrations of dark matter. Gas clouds grew. They became denser. Eventually, some reached critical thresholds where the gas pressure from their own weight began heating their cores. Picture watching a slow-motion collapse. A cloud spanning dozens of light years begins contracting. Over millions of years, it shrinks. The center compresses. Temperature rises from the pressure. All this happens in absolute darkness. No light signals the transformation. The universe remains black. Only gravity reveals the change through its pull on surrounding matter. When core temperatures hit several million degrees, nuclear fusion ignites. Hydrogen fuses into helium. Energy releases. Photons stream outward. Light appears. The first star is born. This solitary point of light breaks the darkness. For the first time since recombination, a fusion-powered beacon shines. The Dark Ages begin to end. These pioneer stars differed radically from what we see today. Lacking any heavy elements to aid cooling, the gas clouds could not fragment into smaller pieces as easily. Stars forming from pure hydrogen and helium tended toward enormous masses. Many likely exceeded 100 times what we would consider normal stellar mass. Some may have reached 300 times that benchmark. Such giants burn incredibly hot. Their surfaces would glow blue-white, with temperatures exceeding 100,000 degrees. They would shine with the brightness of millions of ordinary stars combined. Their lifetimes would be brief by stellar standards, perhaps just a few million years from birth to death. They would transform the universe around them in that short span. The ultraviolet radiation from these first stars began ionizing the surrounding hydrogen gas. Neutral atoms absorbed the energetic photons. Electrons stripped away from nuclei. Ionized regions formed around each new star, bubbles of plasma expanding into the neutral gas. As more stars formed, more bubbles appeared. Eventually, the bubbles merged. Large regions became ionized. This reionization process gradually transformed the entire universe from neutral back to ionized over perhaps 500 million years. The epoch of reionization marks the transition from the Dark Ages to a universe filled with light and structure. Galaxies began forming. Stars clustered together under gravity. The modern universe started taking shape. The discovered galaxy exists right at the boundary between darkness and light. It formed when reionization was just beginning. It somehow assembled itself during the final stages of the Dark Ages. That timing makes its chemical sophistication even more puzzling. There was barely time for even one stellar generation. Oxygen tells a story of violence. This element cannot form in the Big Bang. It cannot form in small stars. It requires the extreme conditions found only in massive stars during their final moments. Finding oxygen in this early galaxy means finding evidence of stellar death, specifically supernovae, repeated multiple times. Every oxygen atom began its existence inside a star's core. Nuclear fusion built it through a sequence of reactions. First, helium fuses to create carbon. 3 helium nuclei collide almost simultaneously, overcoming enormous repulsive forces to bind together. This produces carbon-12, with 6 protons and 6 neutrons. The process happens through an extraordinary coincidence of energy levels that makes carbon formation possible. Once carbon exists, adding another helium nucleus creates oxygen-16. This has 8 protons and 8 neutrons. The reaction releases energy, helping power the star. As fusion continues, carbon and oxygen accumulate in layers within the stellar core. Heavier elements form in shells around them. The star builds an onion-like structure with different elements at different depths. This process continues only in stars massive enough to compress their cores to the required temperatures and densities. Smaller stars like our own cannot achieve the conditions needed. They stop at carbon and oxygen, which remain locked forever in white dwarf remnants. Only stars above roughly 8 times typical mass can proceed further. They fuse oxygen into neon and magnesium. They fuse neon into still heavier elements. Each stage requires higher temperatures and lasts for shorter periods. The final burning stages happen rapidly. Silicon fuses into iron peak elements in just days. Iron accumulates in the core. Then disaster strikes. Iron cannot fuse to release energy. Fusing iron consumes energy instead. The core suddenly loses its pressure support. Gravity wins. The core collapses in less than 1 second. Material falls inward at velocities approaching 1/4 the speed of light. The collapse halts when the core reaches neutron star density. The infalling material rebounds off this incompressible surface. A shock wave forms, racing back outward. The shock wave stalls initially, unable to reverse the infall. Neutrinos streaming from the collapsed core deposit energy into the stalled shock. The shock revives. It plows through the outer layers of the star. Temperature spikes. Elements in those layers undergo final fusion reactions as the shock passes. The star explodes. A core collapse supernova unleashes more energy in seconds than the star emitted during its entire previous lifetime. The explosion tears the star apart. All the oxygen, carbon, neon, magnesium, silicon, and iron produced during the star's life get hurled into space at thousands of miles per second. The heavy elements disperse across dozens of light years. This ejected material mixes with the surrounding interstellar gas. Clouds enriched with oxygen and other heavy elements drift through space. When these enriched clouds collapse to form new stars, those second-generation stars inherit the chemical legacy of their predecessors. Planets forming from the leftover disk also contain these heavy elements. This is how complexity enters the universe. The oxygen detected in the distant galaxy proves that this entire cycle happened multiple times within the first 300 million years. Multiple massive stars formed, lived, fused elements, and exploded. The explosions dispersed oxygen into the surrounding gas. That gas then formed more stars, continuing the enrichment. The cycle repeated enough times to build 10 times more oxygen than models predict should exist at that epoch. The oxygen line in the spectrum glows as a signature of death and rebirth. Stars create elements, but supernovae distribute them. Without these catastrophic explosions, all the carbon, oxygen, and heavier elements forged in stellar cores would remain locked inside remnants forever. Supernovae are the delivery mechanism that makes chemical evolution possible across the universe. The explosion process itself creates additional elements beyond what formed during the star's stable lifetime. As the shockwave plows through the outer layers, it heats material to billions of degrees. At these temperatures, nuclei collide with enormous energy. Rapid fusion reactions create elements that the star never produced during its normal burning phases. Calcium, titanium, and iron peak elements form in significant quantities during these explosive seconds. Consider the energetics involved. A single core collapsed supernova releases approximately 10 to the 50 first power ergs of energy. This number defies comprehension. It equals more energy than the star emitted as light during its entire 10 million year lifetime. It equals more energy than an entire galaxy of stars emits in several seconds. Most of that energy escapes as neutrinos, ghostly particles that barely interact with matter. Even the tiny fraction converted to kinetic energy of the explosion suffices to tear the star apart. The expanding debris travels outward at velocities between 5,000 and 20,000 miles per second. Nothing stops this material. It plows into surrounding gas, creating a shockwave that sweeps up even more material. The supernova remnant expands for thousands of years, eventually merging with the general interstellar medium. The heavy elements become mixed throughout the galaxy, available for incorporation into future generations of stars and planets. Early in cosmic history, these explosions had disproportionate impact. The universe was denser then. Galaxies were smaller. A single supernova could enrich a significant fraction of a dwarf galaxy's gas supply. The first supernovae essentially polluted their entire host systems with heavy elements. This pollution was essential for enabling the formation of smaller, longer-lived stars and eventually planets capable of supporting life. The supernova rate in the early universe remains uncertain. The first generation of stars, formed purely from hydrogen and helium, likely became very massive. Most would have ended as supernovae. If star formation began at 200 million years post-Big Bang and massive stars lived just a few million years, then supernovae could have started occurring by 205 million years. This leaves potentially 85 million years for multiple generations of enrichment before the observed galaxy snapshot. Models attempting to reproduce the observed oxygen abundance struggle with efficiency. How many stars must form and explode to create the detected oxygen levels? How efficiently does the ejected material mix with surrounding gas? How quickly does that enriched gas cool enough to collapse and form new stars? Each question introduces uncertainties. Multiplying uncertainties creates large error bars. Even pushing every assumption to maximize early enrichment, models barely match observations. Some researchers propose that the initial mass function in the early universe, the distribution of stellar masses, was heavily weighted toward massive stars. If nearly all first-generation stars were massive, then nearly all would explode as supernovae, maximizing heavy element production. However, this creates other problems. Massive stars form less efficiently and require significant amounts of gas. Forming enough massive stars quickly enough challenges our understanding of star formation physics. The supernova requirement creates a minimum timescale problem. You need time for stars to form. You need time for them to evolve and die. You need time for the ejecta to disperse and mix. You need time for new stars to form from enriched gas. Every step takes millions of years. The sum total should exceed 100 million years easily. This galaxy exists before that timeline reasonably completes even once, much less multiple times. The heavens reveal their violence through oxygen. The discovery required looking in wavelengths invisible to human eyes. James Webb Space Telescope observes primarily in infrared, detecting heat rather than visible light. This capability makes it uniquely suited to finding the most distant objects in the universe. Light from remote galaxies gets stretched by cosmic expansion. Originally emitted as visible or ultraviolet light, it arrives redshifted into infrared wavelengths. Webb captures this ancient light. The near-infrared camera formed the primary detection instrument. This camera, built under the direction of the University of Arizona, can detect light with wavelengths from 0.6 to 5 microns. For comparison, visible light spans 0.4 to 0.7 microns. The camera sees slightly beyond human vision into the near-infrared. It achieved this sensitivity by cooling its detectors to -388 degrees Fahrenheit, just 33 degrees above absolute zero. At these temperatures, thermal noise decreases enough that faint signals become detectable. The telescope pointed at a region called the J-DES fields. Multiple teams have observed these fields repeatedly, building up deep images through long exposures. The galaxy appeared as a tiny red dot. Its color immediately signaled high redshift. Blue and green wavelengths were completely absent, indicating those wavelengths had been stretched far beyond detection limits. Only the reddest channels showed any signal. Spectroscopy confirmed the distance. Rather than just taking a picture, instruments dispersed the light into a spectrum, spreading different wavelengths across a detector. This spectrum revealed a characteristic pattern called the Lyman break. Hydrogen atoms absorb ultraviolet light at specific wavelengths. In the galaxy's rest frame, this absorption occurs at 121.6 nanometers. That light was emitted 13.5 billion years ago, when the universe was just 2% its current age. Cosmic expansion stretched that wavelength by a factor of 15.3. It arrived at 1.8 microns, firmly in the infrared, but the real surprise came from the mid-infrared instrument. This instrument observes longer wavelengths from 5 to 28 microns. At these wavelengths, specific emission lines from oxygen become detectable. Oxygen ions emit light at particular wavelengths when excited. For this distant galaxy, those emission lines should have been redshifted into MIRI's detection range if oxygen was present. MIRI detected the oxygen line. The signal appeared at 7.7 microns, stretched from its rest wavelength of 0.501 microns by that same factor of 15.3. The line was bright, indicating significant oxygen abundance. This was not a marginal detection, requiring statistical arguments. The oxygen signature blazed clearly in the data. The observations required extraordinary dedication. The team spent 167 hours imaging with the near-infrared camera. They spent 43 hours imaging with MIRI. This totals over 200 hours of precious telescope time, focused on a region of sky smaller than a grain of sand held at arm's length. Such commitment reflects the importance of the target. Only the most distant and most interesting objects warrant this investment. Luck played a role. The galaxy happened to sit in a position perfectly aligned with both instruments' fields of view. If the telescope had pointed just slightly differently, MIRI would have missed the target. The team would never have detected the oxygen. The discovery would have been delayed until future observations. Serendipity combined with skill to capture this snapshot of the infant universe. The infrared detection capability of James Webb, impossible just decades ago, opened a window on cosmic dawn. Older telescopes like Hubble, operating primarily in visible wavelengths, cannot see these ancient galaxies. Their light has shifted too far into the red. Webb's design specifically targets this regime, allowing us to witness the universe in its first few 100 million years for the first time. What we see contradicts what we expected. The technology reveals uncomfortable truths. The galaxy shines too brightly. Objects at such extreme distances should appear faint, barely detectable, even with the most powerful instruments. This one blazes with unexpected intensity. Its brightness exceeds theoretical predictions by factors that cannot be easily explained. Something about the early universe produced exceptionally luminous systems. Luminosity depends fundamentally on stellar mass. Massive stars shine brighter than small stars. A star 100 times more massive than average shines roughly 1 million times brighter. The brightness scales dramatically with mass. If this galaxy contains predominantly massive stars, that could explain the brightness. But forming predominantly massive stars requires special conditions that may not have existed universally. Star formation efficiency also matters. How much of the galaxy's gas mass converts into stars determines total light output. If star formation proceeded with exceptional efficiency, packing more stellar mass into a compact region, the system would shine brighter. Current models of early galaxy formation actually predict low efficiency. Gas in the early universe should have been difficult to cool and collapse efficiently. Observations contradict this prediction. Another possibility involves active galactic nucleus contribution. Perhaps a supermassive black hole already existed at the galaxy's center, accreting material and releasing enormous energy. Black hole accretion can outshine the entire stellar population of a galaxy. However, explaining how supermassive black holes formed so early creates a different problem. These objects typically require hundreds of millions of years to grow to substantial masses through gas accretion or merger of smaller black holes. The specific luminosity value raises eyebrows. The galaxy appears roughly as bright as galaxies 10 times more massive. Either it contains far more stars than its compact size suggests, or those stars are intrinsically much more luminous than typical. Neither explanation fits comfortably with standard models. The first requires packing stellar mass into an implausibly small volume. The second requires unusual stellar populations that should not dominate so completely. Comparisons with nearby galaxies illustrate the paradox. Modern star-forming galaxies with similar stellar masses show predictable brightness ranges. This ancient system exceeds those expectations. It acts like a galaxy that has had billions of years to form stars, not hundreds of millions. The compression of evolutionary timescales appears in multiple properties, not just chemical composition. Dust extinction could be hiding some of the true brightness. Dust in galaxies absorbs ultraviolet and visible light, then remits it as infrared. This shifts energy to longer wavelengths. However, dust consists of heavy elements, primarily carbon and silicon. The early universe lacked sufficient heavy elements to produce significant dust. This galaxy's high oxygen abundance suggests some dust might exist, but probably not enough to dramatically affect observations. The brightness appears intrinsic. Multiple studies have verified the luminosity measurements using different methods. Photometry in various infrared bands consistently shows the same high brightness. Spectroscopic measurements confirm the distances, ruling out contamination from foreground objects. The galaxy really is that bright at that distance. The measurement is solid. The physics is puzzling. Some theorists suggest that early universe star formation may have proceeded in bursts rather than steadily. Perhaps this galaxy caught during an exceptional burst of star formation, temporarily making it far brighter than average. If we observed 100 similar galaxies at this distance, most might appear much fainter, with only a few caught during brightness peaks. However, the limited statistics available so far do not support this interpretation. The few distant galaxies found all show unexpected properties. The luminosity paradox extends beyond this single object. James Webb has found multiple galaxies at similar distances showing elevated brightness. The pattern suggests something systematic about early galaxy formation differed from current expectations. Perhaps the initial conditions, the nature of dark matter halos, or the physics of gas cooling worked differently at those early times. Understanding these differences will require new theoretical frameworks and many more observations. Brightness provides a window into stellar populations. Distance in cosmology is complicated. Light from remote objects has traveled for billions of years to reach us. During that journey, space itself has expanded, stretching the light's wavelength. The amount of stretching, called redshift, tells us the distance. This galaxy has a redshift of 14.3, placing it among the most distant objects ever observed. Redshift works through the Doppler effect combined with cosmic expansion. As space expands, it carries galaxies apart. Light traveling through expanding space gets stretched to longer wavelengths. Redder wavelengths mean lower energy. The more space has expanded during the light's journey, the more stretched the light becomes. We measure this stretching by comparing observed wavelengths to the wavelengths emitted. For this galaxy, every wavelength has been stretched by a factor of 15.3. The number comes from 1 plus the redshift value. Ultraviolet light emitted at 100 nanometers arrives as infrared at 1530 nanometers. Visible light is shifted far beyond detection. Only light emitted as visible or ultraviolet remains detectable at all after this extreme stretching. Converting redshift to distance requires a cosmological model. We must assume values for the universe's expansion rate, matter density, and dark energy density. Current best measurements give a Hubble constant of 67 kilometers per second per megaparsec. With these parameters, a redshift of 14.3 corresponds to a light travel time of 13.4 billion years. The light left this galaxy just 290 million years after the Big Bang. However, the galaxy is now much farther away than 13.4 billion light years. While the light traveled toward us, the universe continued expanding, carrying the galaxy farther. The current proper distance to this galaxy's location is approximately 46 billion light years. We can never visit this location. It recedes faster than light speed due to the expansion of space itself. This extreme redshift places the object firmly in the epoch of reionization. The universe was transitioning from neutral to ionized during this time. The first galaxies were just beginning to form. Structure was emerging from the nearly smooth primordial density field. Observing objects at these distances means witnessing cosmic dawn directly, seeing the universe in its infancy. Measuring such high redshifts requires spectroscopy, not just photometry. Taking a picture shows where an object appears red, but does not precisely determine how red. Spectroscopy spreads the light into its component wavelengths, revealing specific features like emission and absorption lines. These features have known rest wavelengths from laboratory measurements. The observed wavelengths are then divided by rest wavelengths to calculate the redshift factor. For this galaxy, multiple spectral features confirm the redshift. The Lyman break appears at the expected wavelength. Oxygen emission lines appear at wavelengths consistent with that same redshift. Hydrogen emission features align. All the pieces fit together, leaving no doubt about the distance. Independent measurements by different instruments agree. The redshift is secure. Higher redshifts push toward the theoretical limit of what can be observed. At redshift 30 or so, we approach the epoch when the first stars formed. Beyond that lies the Dark Ages, when no stars yet shone. Currently, redshift 14.3 represents near the edge of detection capabilities. A few candidates at redshift 16 or 17 have been reported but require confirmation. This galaxy remains among the most distant, confirmed objects. Every increase in observable redshift reveals earlier cosmic conditions. At redshift 1, we see galaxies as they were 7.7 billion years ago. At redshift 6, we see galaxies from the first billion years. At redshift 14, we see galaxies from the first 300 million years. Each step requires exponentially more powerful instruments. James Webb reaches farther than any previous telescope, but even it cannot see all the way back to the first stars. That will require the next generation of instruments. The redshift number encodes vast expanses of space and time. 14.3 means looking back across more than 97% of cosmic history. It means seeing light that began its journey when the universe was 40 times younger than today. It means witnessing an era when galaxies were just learning to exist. The number is more than a measurement. It is a time machine reading. Metal abundance in astronomy has a specific meaning. Any element heavier than helium counts as a metal. This includes carbon, oxygen, neon, magnesium, silicon, sulfur, and iron. The term sounds strange to chemists, but astronomers use it consistently. This galaxy contains metals at levels 10 times higher than models predict should exist at its epoch. The measurement comes from spectral line strengths. Oxygen ions emit light at specific wavelengths when their electrons transition between energy levels. The brightness of these emission lines relative to hydrogen lines indicates the oxygen to hydrogen ratio. For this galaxy, that ratio exceeds 1 part in 10,000 by oxygen atoms. This sounds tiny, but represents substantial enrichment compared to the primordial composition of essentially zero heavy elements. Solar composition provides a reference point. Material in and around our local star contains roughly 1 part in 500 oxygen atoms compared to hydrogen. This represents the accumulated enrichment from 9 billion years of stellar generations in the galactic disk. The newly discovered galaxy, existing just 300 million years after the Big Bang, already achieved 1/20th of solar metallicity. That represents astonishingly rapid chemical evolution. Computer simulations of early galaxy formation predict much lower metallicities at this epoch. Models typically show metallicities around 1,000th to 1/10,000th of solar values for galaxies at redshift 14. This galaxy exceeds those predictions by an order of magnitude. The discrepancy points to incomplete understanding of early star formation and chemical enrichment processes. The metallicity affects many galaxy properties beyond just chemical composition. Gas with higher metal content cools more efficiently. Metals provide additional pathways for energy to radiate away. More efficient cooling allows gas clouds to fragment into smaller pieces, forming smaller stars. This creates a positive feedback loop where enrichment enables different types of star formation. The early onset of metal enrichment may have accelerated galaxy assembly. Measuring metallicity precisely requires detecting multiple emission lines from different elements. Ideally, astronomers want to measure lines from oxygen, nitrogen, carbon, neon, and sulfur. Ratios between these elements reveal details about which types of stars produce the metals. Unfortunately, at extreme distances, only the brightest lines are detectable. For this galaxy, strong oxygen emission provides the primary metallicity indicator. Other elements remain undetected, but presumably exist at proportional abundances. The oxygen abundance specifically indicates enrichment from massive stars. Core collapse supernovae produce oxygen abundantly. Type Ia supernovae, arising from white dwarf explosions, contribute less oxygen but more iron peak elements. The strong oxygen signature suggests core collapse supernovae dominated the enrichment. This aligns with expectations that massive stars, which explode as core collapse events, dominated early stellar populations. Spatial variations in metallicity would be revealing, but cannot be measured at this distance. The galaxy appears as an unresolved point source, smaller than 1 pixel in the images. We cannot distinguish between a chemically uniform system and one with enriched central regions and pristine outer zones. Such gradients would indicate ongoing enrichment with newly formed stars mixing with older, metal-poor gas. Future observations with better resolution might reveal these details. The high metallicity creates a chicken and egg problem. High metallicity should make star formation more efficient, allowing more stars to form and further increasing metallicity. However, reaching high metallicity in the first place requires substantial prior star formation. The galaxy appears caught in a mature state despite existing in the infant universe. It simultaneously shows properties of youth through its small size and properties of age through its chemical composition. Comparing this object to other high redshift galaxies will establish whether it represents an outlier or a typical example. If many galaxies at similar distances show elevated metallicity, then the models require systematic revision. If this object is unique, then perhaps special circumstances in its environment enabled unusually rapid enrichment. Current statistics are insufficient to distinguish these scenarios. More observations are needed. The metal content whispers of hidden generations. The first stars differed radically from those shining today. They contained absolutely zero metals, formed purely from the hydrogen and helium created in the Big Bang. Astronomers call these hypothetical objects population 3 stars. None have been observed directly, but theory demands they must have existed. This galaxy may preserve evidence of their legacy. Population 3 stars likely grew enormous. Without metals to facilitate cooling, the collapsing gas clouds that formed them could not fragment efficiently. Larger clumps stayed together, forming more massive stars. Theoretical models suggest typical masses between 30 and 300 times what we consider normal. Some may have reached 1,000 times that benchmark, though such extremes remain speculative. These giants would have burned extraordinarily bright and hot. Surface temperatures might exceed 100,000 degrees, making them glow brilliant blue-white. They would emit copious ultraviolet radiation, ionizing the surrounding gas for dozens of light years in every direction. A single population, 3 star, would have shone as brightly as an entire modern galaxy of typical stars. They would have been impossible to ignore, but their lives would be brief. Massive stars burn through their hydrogen fuel rapidly. While a typical star might shine for 10 billion years, these giants would exhaust their cores in just 2 to 5 million years. After hydrogen burning, they would progress through helium burning, carbon burning, oxygen burning, and silicon burning in rapid succession. Each stage would last progressively shorter periods, with the final stages taking mere days or hours. Their deaths would be spectacular. Most would explode as pair instability supernovae, completely disrupting the star, with no remnant left behind. The explosion energy would exceed typical supernovae by factors of 10 or more. The blast would enrich the surrounding gas with the full range of elements forged during the star's life, from carbon to iron and beyond. These explosions would seed their galaxies with the first metals. Some population 3 stars may have collapsed directly to black holes without exploding. If the star exceeds a certain mass threshold, the core collapse produces a black hole that swallows the entire star before a shock wave can develop. These direct collapse events would create black holes of perhaps dozens to hundreds of solar masses immediately. No enrichment would occur from these events, but the black holes would persist and potentially grow through accretion and mergers. Evidence for population. 3 stars remains indirect. We have never seen one directly. They existed too early and at too great a distance for current instruments to resolve individual stars. Instead, we infer their existence from the chemical patterns in later generation stars. The older stars we can observe in nearby dwarf galaxies show enhancement patterns consistent with enrichment by pair instability supernovae, suggesting population 3 progenitors. This galaxy may have contained population 3 stars during its earliest phases. If star formation began at 200 million years post-bang, and this snapshot comes at 290 million years, then any population 3 stars formed initially have already died. Their explosions enriched the gas from which second and third generation stars then formed. The observed oxygen abundance represents the cumulative output of these early generations. Alternative scenarios exist. Perhaps extremely massive black holes formed early through direct collapse of gas clouds without forming stars first. These black holes might have accreted rapidly, growing to supermassive sizes within a few 100 million years. Their accretion disks would have emitted intense radiation, possibly photo-evaporating the surrounding gas and suppressing further star formation. Such processes might accelerate the apparent evolution of galaxies. The population 3 question remains one of the most fundamental, unsolved problems in astrophysics. When did they form? How massive were they typically? How did they die? How efficiently did they enrich their environments? Each answer constrains our understanding of cosmic evolution. This galaxy, existing in the epoch when population 3 stars should have just finished their work, offers a crucial laboratory for testing theories. Its properties must somehow connect to the nature of those mysterious first stars. The unseen first generation casts long shadows. Galaxies should not assemble this quickly. Current theory describes a hierarchical process where small structures form first, then gradually merge to build larger systems over billions of years. This bottom-up assembly takes time. Small dark matter halos form first, accreting gas and forming stars. These small galaxies then collide and merge, building progressively larger galaxies. The process should be ongoing throughout cosmic history. This galaxy appears to have skipped steps. It shows properties of a mature system, despite existing when the universe barely had time to begin structure formation. The size, mass, and metallicity all suggest a system that has experienced substantial evolution. Yet, the timeline allows only a brief window for that evolution to occur. Something about early conditions enabled dramatically accelerated assembly. Dark matter plays a central role in structure formation. Dark matter does not interact with light or normal matter except through gravity. In the early universe, dark matter could collapse without being hindered by radiation pressure. It formed the gravitational scaffolding upon which normal matter later accumulated. Small dark matter halos emerged first, their enhanced gravity pulling in hydrogen and helium gas. When gas densities became high enough, stars ignited. The formation of these first dark matter halos depended on tiny density fluctuations imprinted during cosmic inflation. Regions that were slightly denser than average attracted more material through gravity. They grew denser still, accelerating the infall. Eventually, these overdense regions collapsed into bound structures separate from the overall expansion of the universe. The timing of this collapse depended on the amplitude of the initial density fluctuations. Measurements of the cosmic microwave background radiation constrain the amplitude of primordial density fluctuations precisely. These measurements indicate that the first halos massive enough to form galaxies should not have collapsed until at least 100 million years after the Big Bang, possibly 200 million years. This delay comes from the requirement that fluctuations must grow to sufficient amplitude to overcome the expansion. Once dark matter halos formed, gas still needed time to cool and collapse within those halos. Hot gas has pressure that resists gravitational collapse. For cooling to occur, the gas must radiate energy away. In primordial gas with no metals, cooling proceeds only through atomic hydrogen transitions. This process is relatively inefficient. Models suggest gas cooling timescales of dozens of millions of years in the first dark matter halos. After cooling, the gas must collapse further to reach densities where star formation occurs. This collapse takes additional time. Fragmentation of the gas cloud creates denser cores where individual stars will form. Turbulence in the collapsing gas creates complex density structures. The whole process, from initial halo formation to active star formation, should require 50 to 100 million years under conventional assumptions. This timeline becomes even more constrained when considering chemical enrichment. The first stars formed from primordial gas. They lived, died as supernovae, and dispersed metals. The enriched gas then needed to mix and cool again before forming second-generation stars. Second-generation stars also lived and died, further enriching the medium. This cycle repeated multiple times to achieve the observed metallicity. Each cycle adds millions of years. Researchers have proposed various mechanisms to accelerate early galaxy formation. One idea suggests that supermassive black holes formed very early through direct collapse. Then their radiation pressures compressed surrounding gas, triggering rapid star formation. However, explaining how black holes massive enough to have significant impact formed so early creates its own difficulties. Black hole seeds would have had to grow by factors of millions through accretion, requiring sustained feeding rates at the theoretical maximum. Another possibility involves extremely efficient star formation. If essentially all gas in the early dark matter halos converted to stars, rather than just a small percentage, then the galaxy could build up stellar mass rapidly. However, feedback processes normally limit star formation efficiency. Supernova explosions heat and expel gas, temporarily halting further star formation. Radiation from massive stars ionizes surrounding gas, increasing pressure and resisting collapse. These feedback processes should have been especially strong in the small halos that formed first. The rapid formation challenge appears in multiple properties simultaneously. The galaxy is too bright, too chemically evolved, too extended, and too massive for its age. Each property individually might be explained by pushing theoretical assumptions to their limits. Explaining all properties together requires either fundamentally rethinking early galaxy formation or accepting that this object is an extraordinary outlier whose properties may never be explained by standard models. Theory meets uncomfortable reality. Time becomes the crucial constraint. Each stellar generation requires a minimum duration from birth through death to dispersal of heavy elements. Adding up these durations reveals whether sufficient time existed for the observed enrichment. The arithmetic paints a problematic picture. Start with the formation time for first-generation stars. Gas must collapse from low-density clouds, spanning dozens of light-years down to stellar cores, just millions of miles across. This compression factor exceeds 1 trillion. Even under gravity's relentless pull, the process takes time. Gas falling inward encounters pressure resistance as density increases. Magnetic fields thread through the collapsing cloud, providing additional support. Turbulence creates irregular density structures that resist smooth collapse. Simulations of primordial star formation suggest collapse timescales between 1 million and 10 million years from the initial formation of a dark matter halo to the ignition of fusion in the first star's core. This range depends on the mass of the dark matter halo and the efficiency of cooling. More massive halos collapse faster. Better cooling allows faster contraction, even pushing assumptions toward rapid formation. The process requires at least 1 million years. Once formed, massive first-generation stars have lifetimes inversely proportional to their mass cubed. A star 30 times the reference mass lives approximately 1/30th cubed, or 1/27,000th, as long as the reference. If we assume a reference lifetime of 10 billion years, then a 30 solar mass star lives roughly 370,000 years. A star 100 times the reference mass lives just 100,000 years. A star 300 times the reference mass might live only 30,000 years. These short lifetimes are actually helpful for rapid enrichment. The sooner stars die and disperse their contents, the sooner second-generation stars can form. However, there is a minimum stellar lifetime that cannot be circumvented. Even the most massive stars require time to burn through their hydrogen, helium, and heavier element fuels. Skipping these stages is not physically possible. The nuclear reaction rates depend on temperature and density in ways that impose speed limits. After the star explodes as a supernova, the ejector must travel outward and mix with surrounding gas. The expanding debris shell reaches velocities of thousands of miles per second. It takes thousands of years for this material to travel dozens of light years and begin mixing with the ambient medium. Eventually, the supernova remnant merges with the general interstellar medium, delivering its payload of heavy elements across a region spanning hundreds of light years. The enriched gas must then cool before forming second-generation stars. Gas, heated by supernova explosions to millions of degrees, requires time to radiate away that energy and return to temperatures where collapse can occur. With only hydrogen and trace metals available for cooling, this process takes millions of years. The presence of metals actually accelerates cooling by providing additional radiative pathways, but early in cosmic history, metal abundances were low enough that cooling remained slow. Second-generation star formation then proceeds, much like first generation, requiring another 1 to 10 million years for collapse. Second-generation massive stars live their brief lives, again just hundreds of thousands of years. They explode, dispersing additional metals. The cycle repeats. Each iteration requires roughly 2 to 20 million years total, dominated by the cooling and collapse timescales rather than stellar lifetimes. To reach the observed metallicity requires perhaps 3 to 10 such cycles, depending on the efficiency of each enrichment episode and the mass distribution of stars formed. 3 cycles at 20 million years. Each totals 60 million years minimum. 10 cycles could require 200 million years. These estimates put the required enrichment time close to or exceeding the available time budget of 100 to 200 million years. The calculations assume favorable conditions at every step. Any delays accumulate. If dark matter halos formed late in the allowed window, or if cooling proceeded slowly, or if star formation occurred in brief bursts separated by long quiescent periods, then the timeline extends. Realistic models typically require longer than minimum estimates because multiple physical processes must coordinate, and each has inherent timescales that cannot be compressed arbitrarily. One potential solution involves overlapping generations. Rather than waiting for one generation to completely finish before starting the next, perhaps multiple generations formed nearly simultaneously in different regions of the proto-galaxy. Gas in some areas might remain pristine and form population 3 stars, even while other regions, already enriched by earlier supernovae, formed second-generation stars. This parallel processing could reduce the total elapsed time. However, parallel processing requires sufficient spatial extent. For different regions to evolve independently, they must be separated by enough distance that enrichment from supernovae in one region takes time to affect other regions. This introduces light travel time delays that still enforce minimum durations. Information and material cannot travel faster than light. Even enrichment signals, moving at substantial fractions of light speed, require thousands of years to cross galactic distances. The generational time calculation strongly suggests that conventional models underestimate how quickly early star formation and enrichment proceeded. Either the timescales are shorter than current estimates, or the efficiency is higher. or both? Determining which possibilities apply requires better understanding of the physical processes governing star formation and feedback in the extreme conditions of the early universe. Every generation leaves its chemical signature. Supernovae do more than create elements. They violently distribute those elements across vast distances, seeding future stellar generations. Without this explosive dispersal, heavy elements would remain locked in stellar remnants, inaccessible to the broader universe. The violence is essential for chemical evolution. A core collapse supernova releases energy equivalent to the entire luminous output of 1 billion galaxies concentrated into a few seconds. Most energy escapes as neutrinos, which barely interact with matter. Still, the tiny fraction converted to kinetic energy of the explosion suffices to accelerate several times the mass of a typical star to thousands of miles per second. Nothing can contain this violence. The outer layers of the star get ejected into space at velocities approaching 1% the speed of light. The expanding debris creates a shock wave in the surrounding medium. The shock front compresses and heats the ambient gas ahead of it. This shocked gas glows with X-rays and optical emission, creating the spectacular supernova remnants we observe today in nearby galaxies. Young supernova remnants, like Cassiopeia A in the Milky Way, show intricate structures created by instabilities in the expanding shock. Dense clumps of ejecta penetrate farther than average, creating finger-like protrusions. Rayleigh-Taylor instabilities mix ejecta with swept-up material. The heavy elements dispersed by supernovae do not spread uniformly. Ejecta from the inner regions of the exploding star, richest in oxygen and heavier elements, often form clumps that travel together. These clumps can remain chemically distinct for thousands of years before fully mixing with the interstellar medium. Observations of supernova remnants reveal spatially varying composition, with some regions enhanced in oxygen, others in silicon, and still others in iron. In the early universe, supernova dispersal had unique characteristics. The proto-galaxies were smaller and denser than modern galaxies. A single supernova could impact a much larger fraction of the total gas supply. The blast wave from one explosion might sweep through the entire system, enriching everything. This enhanced the efficiency of chemical evolution. Every supernova had maximum impact because there was less volume to fill with ejecta. However, this efficiency came with a cost. Energetic supernova explosions could expel gas entirely from small dark matter halos. If the explosion energy exceeded the gravitational binding energy of the halo, the material would escape to intergalactic space. Early galaxies likely lost substantial fractions of their gas through this supernova-driven outflow. The most vigorous star-forming systems might have blown themselves apart, halting further star formation. Only halos massive enough to retain their gas, despite supernova feedback, could continue forming stars. Multiple supernovae occurring in close temporal succession would amplify these effects. If dozens of massive stars formed in a single burst, they would die within a few million years of each other, all as supernovae. The combined energy from multiple overlapping explosions could create a superbubble of hot gas that breaks through the galaxy's outer layers and vents into intergalactic space. This runaway feedback process might have regulated early star formation, preventing systems from forming stars too efficiently. The velocity of ejected material affects how quickly enrichment proceeds. Faster ejecta travel farther before slowing down and mixing with ambient gas. Typical supernova ejecta velocities range from 3,000 to 10,000 miles per second. At these speeds, material travels 1 light-year in approximately 60 to 200 years. To disperse across a proto-galaxy spanning perhaps 1,000 light-years requires tens of thousands of years. This represents a lower limit on the dispersal timescale. Mixing proceeds through turbulence and instabilities. The shock front develops ripples and irregularities that grow over time. Vortices form, eddies circulate. These motions stir ejecta into the surrounding medium, breaking up large-scale clumps into smaller fragments. Eventually, the composition becomes relatively uniform across the affected region. However, reaching complete homogeneity takes time. Even after millions of years, traces of inhomogeneity can persist. In a galaxy experiencing multiple generations of star formation and enrichment, the interstellar medium develops a complex chemical structure. Different regions have different metallicities depending on their enrichment history. Gas near concentrations of massive stars shows higher metallicity. Gas in voids between star-forming regions remains more pristine. Stars forming from this inhomogeneous medium inherit varied chemical compositions, creating the metallicity distribution function observed in stellar populations. The discovered galaxy must have experienced numerous supernovae to achieve its observed metallicity. Each supernova contributed its share of oxygen and other elements. The cumulative effect, integrated over perhaps dozens to hundreds of individual explosions, produced the chemical signature detected by James Webb. Every explosion was a step in the progression from primordial purity to chemical complexity. The violent dispersal enabled the transformation. Chaos creates the conditions for order. Models predicted a different universe. Computer simulations of galaxy formation, refined over decades using observations of the modern cosmos, consistently produce galaxies that assemble hierarchically over billions of years. Small objects form first and gradually merge to build larger structures. In these models, galaxies at 300 million years post-bang should be tiny, dim, and chemically primitive. The observations show otherwise. The standard model of galaxy formation builds on cold, dark matter cosmology. Dark matter provides the gravitational scaffolding that holds galaxies together. Its density fluctuations, inherited from quantum fluctuations during cosmic inflation, determine where structure forms. Higher density peaks collapse first, forming the earliest dark matter halos. Baryonic matter, normal hydrogen and helium gas, falls into these halos and eventually forms stars. Simulations begin with initial conditions taken from cosmic microwave background measurements. These conditions specify the distribution and amplitude of density fluctuations when the universe was 380,000 years old. The simulation then follows the gravitational evolution forward in time. Dark matter particles attract each other gravitationally. Gas particles experience both gravity and pressure forces. Star formation occurs when gas exceeds threshold densities. Supernovae inject energy back into the gas, regulating further star formation. These simulations successfully reproduce many observed properties of galaxies today. They explain the clustering of galaxies, the rotation curves of spiral galaxies, the colors and morphologies of different galaxy types, and the cosmic star formation history. The success of these models gives confidence that the fundamental physics is correct. Yet when extrapolating back to the first few 100 million years, the models clearly fail. The failure appears in multiple ways. Models predict that at redshift 14, the most massive collapsed dark matter halos should contain around 100 million times the reference mass in dark matter. These halos would gravitationally attract roughly 1/6 that mass in baryonic matter, given cosmic baryon fractions. This sets the gas supply available for forming stars. Even converting all available gas into stars yields a galaxy less massive and less luminous than observed. Star formation efficiency provides a possible adjustment. Perhaps early galaxies converted a much larger fraction of their gas into stars than modern galaxies do. However, feedback processes should have been stronger in the early universe, not weaker. The first massive stars exploded as energetic supernovae, heating and expelling surrounding gas. Radiation from these stars ionized the gas, increasing its pressure and resisting further collapse. These effects should have suppressed star formation, not enhanced it. Chemical enrichment rates in models proceed too slowly. Even when maximizing the formation rate of massive stars and assuming all of them explode as supernovae, the simulations produce metallicities far below the observed value at redshift 14. The bottleneck is the time required for each generation. Gas must cool, collapse, form stars, wait for those stars to evolve and die, then wait for ejecta to disperse and the gas to cool again. Each cycle requires at least several million years, often tens of millions. Multiple cycles needed to build observed metallicity simply do not fit within the available timeline. Some researchers suggest the initial mass function was fundamentally different in the early universe. Perhaps stars forming from primordial gas were biased strongly toward massive stars, with very few low-mass stars. This would maximize supernova rates and heavy element production. However, theoretical models of star formation from primordial gas actually suggest a top-heavy mass function naturally emerges, and simulations already incorporate this assumption. Even with all first-generation stars being massive, the enrichment proceeds too slowly. Another proposed solution involves mixing between enriched and pristine gas. Perhaps small patches enriched by early supernovae became the preferred sites for subsequent star formation, creating locally enhanced metallicities while leaving most gas pristine. However, spectroscopic observations probe the integrated properties of the entire galaxy. If only small regions were highly enriched, the observed emission lines would be weaker, corresponding to lower average metallicity. The observations indicate substantial enrichment across the system. Modified dark matter properties offer a radical alternative. If dark matter interacts with itself through forces beyond gravity, this could affect the collapse timescales and structure of dark matter halos. Self-interacting dark matter models change the density profiles of halos, potentially accelerating galaxy formation. However, such models face constraints from observations of galaxy clusters and other large-scale structures. Modifications required to explain the early galaxy results may conflict with constraints from the late universe. The cumulative failures suggest that current models miss some critical physics relevant in the early universe. Perhaps the star formation process operated fundamentally differently at high redshift. Perhaps dark matter halos assembled through mechanisms not included in simulations. Perhaps feedback processes had different effects in the extreme conditions of infant galaxies. Identifying which modifications are required and validating them through additional observations represents a major challenge for the field. The observations have delivered their verdict. Radio telescopes see the universe differently. While James Webb observes infrared light, the Atacama Large Millimeter Array in Chile detects radio waves with wavelengths measured in millimeters. This complementary view provides independent confirmation of the oxygen detection. Two separate teams analyzed ALMA data, and both found the same conclusive signature. ALMA consists of 66 radio antennas spread across the high desert plateau of northern Chile. At an elevation of 16,000 feet, the facility sits above much of Earth's atmosphere, reducing interference from water vapor. The antennas work together as an interferometer, combining their signals to create images with resolution far exceeding what any single antenna could achieve. The array can simulate a telescope miles across. Oxygen atoms emit radio waves at a specific frequency when electrons transition between energy levels. The fine structure transition of doubly ionized oxygen occurs at a rest frequency of 880 GHz, corresponding to a wavelength of 0.34 millimeters. For a galaxy at redshift 14.3, cosmic expansion stretches this wavelength by a factor of 15.3. The emission arrives at 57 GHz, well within ALMA's detection range. The observation required exceptional sensitivity. Radio emission from distant galaxies is inherently faint. Collecting enough photons to create a detection demands long integration times. ALMA pointed at the target for dozens of hours across multiple observation sessions. Data from different antennas were carefully calibrated and combined. Atmospheric fluctuations and instrumental effects were corrected. Slowly, signal emerged from noise. The first team, led by Dutch researchers, analyzed data from one observing campaign. They identified a clear emission line at precisely the frequency predicted for oxygen from this galaxy. The line width indicated the velocity dispersion of gas within the system, providing information about dynamics and mass. The line intensity revealed the total amount of oxygen present, confirming the high metallicity. The second team, led by Italian researchers, independently analyzed data from different observations. They found the identical emission line at the same frequency with consistent intensity. The agreement between independent analyses eliminated concerns about systematic errors or data processing artifacts. The oxygen detection was real. ALMA's confirmation provided more than validation. Radio observations measured different properties than infrared observations. The radio emission traces cold molecular gas, the fuel for future star formation. The line shape reveals gas kinematics, how material moves within the galaxy. These measurements complement the stellar population information from James Webb, building a complete picture of the system. The oxygen line detection also enabled an extraordinarily precise distance measurement. Radio spectroscopy achieves much higher spectral resolution than infrared spectroscopy. The line frequency can be measured to many significant figures. This translates to a redshift uncertainty of just 0.005%. Few objects at any distance have such precisely determined redshifts. The measurement pins down the galaxy's location in space and time with negligible error. Multiple teams using multiple telescopes observing at multiple wavelengths all see consistent properties. The galaxy exists at the claimed distance. It contains the claimed amount of oxygen. It shines with the claimed brightness. No single measurement could carry this weight alone. The convergence of independent observations builds ironclad confidence in the results. ALMA's contribution extends beyond this single galaxy. The facility has begun systematic surveys of high redshift galaxies, measuring their gas content and chemical composition. These surveys will reveal whether the discovered galaxy is unique or representative of a broader population. If many galaxies at similar distances show elevated oxygen abundances, the theoretical challenge intensifies. If this object stands alone, then understanding its special circumstances becomes paramount. Radio astronomy and infrared astronomy together paint a fuller picture than either could alone. Different wavelengths reveal different physical processes. Combining insights across the electromagnetic spectrum provides the comprehensive understanding necessary to unravel cosmic mysteries. This galaxy, visible to humanity through multiple windows simultaneously, offers a rare opportunity to witness cosmic dawn in exceptional detail. Independent confirmation eliminates doubt. Precision matters in cosmology. Knowing a galaxy's distance to high accuracy determines its place in cosmic history with certainty. The oxygen line detection by ALMA achieved a measurement precision unprecedented for objects at such extreme distances. The redshift uncertainty of 0.005% corresponds to a timing uncertainty of just 1 million years in a universe nearly 14 billion years old. This precision comes from the narrow width of spectral lines combined with the high resolution of radio spectroscopy. When gas in a galaxy emits at a specific wavelength, the emission is not infinitely sharp. Random thermal motions of atoms broaden the line through the Doppler effect. Atoms moving toward us emit at slightly shorter wavelengths. Atoms moving away emit at slightly longer wavelengths. The combination creates a line with finite width. For this galaxy, the oxygen line width corresponds to velocity dispersions around 200 miles per second. This indicates the typical speeds of gas clouds moving within the system. The width is much smaller than the redshift itself, which corresponds to velocities approaching the speed of light. The line center can therefore be determined accurately, despite the finite width. Fitting a profile to the observed line shape locates the central wavelength precisely. ALMA's spectral resolution allows measurement of wavelengths to parts in 1 million. The receiver technology and correlator systems process the incoming signals with extremely high fidelity. Instrumental effects are well characterized and corrected. The result is a spectrum where the oxygen line position can be measured to a precision of just a few megahertz out of 57 gigahertz, or about 1 part in 10,000. Converting wavelength precision to distance precision requires accounting for cosmological expansion. The relationship between redshift and distance depends on the expansion history of the universe. This history is determined by the matter density, dark energy density, and Hubble constant. While uncertainties exist in these cosmological parameters, they contribute negligibly compared to the precision of the redshift measurement itself. The dominating error comes from the line measurement, which is now minimal. Previous distance measurements to galaxies at similar redshifts relied on photometric techniques. These methods measure brightness in several broad wavelength bands and fit the observed colors to models. Photometric redshifts have typical uncertainties of several percent. A 3% uncertainty at redshift 14 corresponds to roughly 40 million years of cosmic time. The improvement achieved through spectroscopy tightens the constraint by a factor of 1,000. The precise distance measurement has immediate scientific value. It allows exact placement of the galaxy on the cosmic timeline. Researchers can now say with confidence that the galaxy existed at 293 million years after the Big Bang, not 280 or 310. This precision enables direct comparison with theoretical models that predict galaxy properties as functions of cosmic time. Discrepancies cannot be attributed to distance uncertainties. Furthermore, the precise redshift enables planning of follow-up observations at other wavelengths. Knowing exactly where to tune instruments maximizes sensitivity to other emission lines. Carbon monoxide emission, for instance, traces molecular gas and should appear at predictable frequencies given the confirmed redshift. Hydrogen emission lines should appear at calculable wavelengths. Each additional detection builds a richer understanding of the system's properties. The measurement also serves as a calibration point for other techniques. Photometric redshift methods can be tested against this secure spectroscopic measurement. If photometric methods systematically over- or underestimate redshifts at high values, the discrepancy reveals biases that must be corrected. Accurate spectroscopic redshifts for high redshift galaxies remain rare. Each new measurement improves the calibration of less precise methods. Statistical studies of early galaxy populations benefit from precise distances. Measuring the density of galaxies as a function of cosmic time requires knowing their distances accurately. If distance uncertainties are large, galaxies get scattered across different time bins, washing out evolutionary trends. With precise distances, each galaxy sits firmly in its proper time bin. Population statistics become sharper. Evolutionary trends emerge more clearly. The technical achievement deserves recognition. Detecting faint emission from objects at the edge of the observable universe, then measuring that emission's wavelength to parts in 10,000 represents extraordinary observational capability. The precision results from decades of technological development in receiver design, antenna construction, signal processing, and atmospheric correction. Every improvement in these systems enables new science. The precise distance turns an interesting discovery into a fixed point in cosmic history. The galaxy no longer floats in an uncertain era. It stands at an exact moment in the universe's youth. That moment challenges our theories. The precision ensures the challenge is real. Cosmic dawn marks when the first stars ignited, ending the Dark Ages. Before this discovery, astronomers believed dawn occurred around 200 to 400 million years after the Big Bang. This galaxy forces revision of that timeline. If substantial star formation and chemical enrichment already occurred by 290 million years, then the first stars must have formed significantly earlier. The reasoning follows from stellar evolution timescales. The oxygen observed in this galaxy required multiple generations of massive stars. Each generation needed time to form, burn its fuel, and explode. The ejecta needed time to disperse and mix. The enriched gas needed time to cool and collapse again. Summing these durations gives a minimum time requirement of perhaps 50 to 100 million years between the formation of first stars and the observed galaxy state. If the galaxy was observed at 290 million years and required 100 million years of prior evolution, then the first stars must have formed by 190 million years at the latest. Some estimates push first star formation even earlier, to perhaps 150 million years post-bang. This compresses the dark ages considerably, leaving less time between recombination at 380,000 years and the end of darkness. Why does earlier star formation matter? It constrains the physics of structure formation. Dark matter density fluctuations needed time to grow to amplitudes sufficient for collapse. Gas needed time to fall into dark matter halos and cool. If all this happened faster than expected, then either the initial density fluctuations were larger than measured, or the collapse proceeded more efficiently than modeled, or both. The cosmic microwave background measurements place tight constraints on the amplitude of initial density fluctuations. These measurements come from multiple satellites, including Planck, and are extraordinarily precise. Substantial changes to the initial fluctuation spectrum would conflict with observations. Therefore, blaming early star formation on larger initial fluctuations seems unlikely. The answer must lie in how structure collapsed and evolved. Enhanced efficiency of dark matter collapse could result from modified dark matter properties. Standard cold dark matter is collisionless and non-interacting except through gravity. If dark matter has weak self-interactions or couples to unknown fields, its collapse behavior could differ. Such modifications are speculative but not ruled out by current observations. They would need careful fine-tuning to match all existing constraints while explaining early structure formation. Alternatively, baryonic physics might operate differently in the extreme conditions of the early universe. Gas cooling at very high redshift proceeds in a dense environment with intense radiation fields from the first stars. This radiation can dissociate molecules, heat gas, and ionize atoms. The interplay between cooling and heating determines when and where gas can collapse to form stars. Perhaps this balance shifted toward more efficient star formation than current models assume. Population. 3 stars themselves might have been more common or more massive than theories predict. If the initial mass function was extremely top-heavy, with nearly all stars forming above 50 times the reference mass, then the supernova rate and metal production would maximize. Such a mass function would require understanding why fragmentation of collapsing gas clouds failed to produce smaller stars. The physics of fragmentation in metal-free gas remains uncertain and may allow for this possibility. Early galaxy formation scenarios now must incorporate rapid enrichment as a requirement rather than a curiosity. Models that produce low metallicity galaxies at redshift 14 are now ruled out by observations. The models must be adjusted until they reproduce the high metallicity. This may require changing star formation prescriptions, supernova feedback implementations, or gas mixing efficiencies. Each change has consequences that propagate through the entire simulation, affecting predictions at later times. The implications extend beyond galaxy formation. The reionization process depended on ultraviolet photons from early galaxies. If galaxies formed earlier and contained more massive stars producing more ultraviolet radiation, then reionization could have proceeded differently than thought. The timeline and topology of reionization bubbles would change. These changes must remain consistent with observations of the ionization state of the intergalactic medium at various redshifts. Pushing cosmic dawn backward also affects the formation of supermassive black holes. These objects, now known to exist in many distant galaxies, require time to grow to their observed masses. Starting black hole formation earlier provides more time for growth through gas accretion and mergers. This may ease the severe theoretical difficulties in explaining billion-mass black holes at redshift 7. Every extra 100 million years of growth time helps. The universe apparently wasted no time organizing itself. Structure formation began as soon as physically possible and proceeded at maximum pace. The Dark Ages were brief. The age of stars and galaxies arrived quickly. Our observations now push back the frontier of that first light, revealing an infant universe already surprisingly mature. How much earlier dawn can be pushed remains an open question. Future observations of even more distant galaxies will tell. The timeline compresses toward impossibility. The galaxy is not just bright and enriched, it is also surprisingly large. At 1600 light-years across, it exceeds expectations for a galaxy so early in cosmic history. Young galaxies should be compact, not extended. The size presents another challenge to formation models, already struggling with luminosity and metallicity. Size relates directly to the mass of the dark matter halo hosting the galaxy. Larger dark matter halos have deeper gravitational potential wells that extend over larger volumes. Gas falling into these halos fills a larger region before becoming dense enough to form stars. The final stellar distribution reflects the initial gas distribution. To produce a galaxy 1600 light-years across requires a dark matter halo, significantly more massive than models predict should exist at redshift 14. The size measurement comes from analysis of the James Webb images. Even at enormous distance, the galaxy appears slightly fuzzy rather than perfectly point-like. This fuzziness, when carefully measured and corrected for instrumental effects, reveals the true spatial extent. The galaxy subtends an angle of approximately 0.07 arcseconds on the sky. Given the cosmological distance, this angular size corresponds to the 1600 light-year physical size. For comparison, the smallest galaxies observed locally, called dwarf spheroidals, span just a few hundred light-years. These tiny systems contain relatively few stars and have low masses. The discovered high redshift galaxy matches or exceeds many nearby dwarf galaxies in size, despite existing when the universe was 2% its current age. This similarity suggests remarkable early development. Extended structure implies lower density. If the same stellar mass were packed into a smaller volume, the galaxy would appear more compact and presumably brighter per unit area. The extended nature means the stars are spread out. This distribution affects how efficiently star formation can continue. More extended systems have lower gas densities, potentially slowing the rate at which new stars form. Yet this galaxy shows strong ongoing star formation based on its emission line properties. The size also affects how feedback operates. Supernova explosions in compact systems concentrate their energy in a small volume, potentially heating gas to temperatures where it escapes entirely. In more extended systems, the same explosion energy distributes over a larger volume, heating the gas less severely. Extended systems may retain their gas better despite vigorous star formation and supernova activity. This could enable sustained star formation and chemical enrichment. However, forming an extended system early requires assembling substantial mass quickly. Dark matter halos grow hierarchically through mergers of smaller halos. A massive halo hosting an extended galaxy at redshift 14 would have assembled from dozens or hundreds of smaller proto-halos. These mergers take time. The merger rate depends on the abundance of nearby halos and the cross-section for gravitational capture. Achieving a sufficiently massive halo by 300 million years post-Bang strains hierarchical assembly models. Alternative scenarios invoke more violent processes. Perhaps the galaxy underwent a major merger shortly before observation. When two substantial galaxies collide and merge, the merger can trigger intense star formation while creating extended tidal structures. The observed galaxy might represent the product of such a recent merger, with its size reflecting tidal disruption rather than smooth assembly. However, major mergers at such high redshift should be rare, simply due to the small number of massive galaxies available to merge. Internal structure would reveal formation mechanisms but cannot be observed at current resolution. If the galaxy has a dense core with more diffuse outer regions, it suggests inside-out formation with a compact central region forming first. If the density is more uniform, it suggests relatively simultaneous formation across the system. If there are multiple clumps, it could indicate a recent merger or fragmented formation. Future observations with better spatial resolution may resolve these details. The extended size may be common among galaxies at this epoch, or may be specific to this object. Statistics remain too sparse to draw conclusions. As more galaxies at similar distances are discovered and measured, patterns will emerge. If all early galaxies prove to be extended, then theories must explain why compact formation is rare, despite seeming more natural. If extended systems are uncommon, then understanding what made this one different becomes the focus. Size serves as a diagnostic of gravitational potential. Measuring sizes of many high redshift galaxies will map the distribution of dark matter halo masses at early times. This distribution tests cosmological models and dark matter properties. Any deviation from predictions based on cold, dark matter, and standard cosmology would point toward new physics. The size anomaly of this single galaxy may be the first hint of such deviations. The galaxy sprawls where it should huddle. This galaxy does not stand alone. James Webb has discovered multiple objects at comparable distances showing similarly extreme properties: bright galaxies, massive galaxies, chemically evolved galaxies. Each discovery adds weight to the conclusion that rapid evolution was commonplace rather than exceptional in the early universe. One galaxy, found at redshift 13, shows emission lines indicating vigorous star formation. Its brightness suggests stellar mass comparable to what modern galaxies required billions of years to assemble. Spectroscopy reveals emission from multiple elements, including oxygen, carbon, and neon. The relative abundances match enrichment by core collapse supernovae, consistent with a population dominated by massive stars. This galaxy reinforces the pattern of precocious development. Another system at redshift 12 appears unusually red for its distance. Red colors typically indicate older stellar populations, where massive blue stars have already died, leaving only longer-lived red stars. Finding such a population at such high redshift implies even earlier star formation. If red stars require billions of years to dominate a stellar population, their presence less than 500 million years after the Big Bang forces star formation back into the first 100 million years. Collectively, these discoveries form a pattern. High redshift galaxies, observed by James Webb, consistently exceed expectations based on pre-launch models. They are brighter, more massive, more chemically enriched, and more evolved than predicted. The discrepancy appears systematic rather than representing occasional outliers. The models failed to capture essential physics governing early galaxy formation. Statistical analyses of the James Webb High Redshift sample reveal additional puzzles. The number density of massive galaxies at redshift 10 to 15 exceeds extrapolations from lower redshift observations by factors of several. This implies that galaxy number densities evolved differently than expected. Either many bright galaxies existed early but later disappeared, or the extrapolation methods were flawed, or both. Explaining the high number density challenges theoretical explanations. Some researchers argue that not all claimed high redshift galaxies are truly at the extreme distances indicated by photometry. Photometric redshift estimates can be fooled by dusty lower redshift galaxies masquerading as distant objects. Dust absorbs blue light and remits it in the infrared, creating red colors that mimic high redshift galaxies. Spectroscopic confirmation is needed to be certain of distances. However, multiple objects now have secure spectroscopic redshifts, confirming their extreme distances. These confirmed cases show the same puzzling properties as the broader photometric sample. Unless all the confirmed cases happen to be the most extreme outliers, while typical objects remain undetected, the problem persists. Skepticism cannot explain away observations. Once spectroscopy validates distances, the pattern extends to multiple measurable quantities simultaneously. Galaxies that are unexpectedly bright also tend to be unexpectedly massive and unexpectedly enriched. The correlations suggest an underlying connection. Perhaps efficient star formation produces all these properties together. A system that converts gas to stars efficiently becomes massive quickly, shines brightly from the many stars, and enriches rapidly due to the high supernova rate from massive stars. Efficiency may be the key. Comparisons between different surveys help assess selection effects. James Webb surveys targeting different regions of sky with different depths and wavelength coverage should find consistent populations if the detections are real and representative. So far, independent surveys find similar objects, supporting the conclusion that bright, high redshift galaxies are genuinely common. The population is real. Follow-up observations are targeting the most interesting objects to measure additional properties. Detecting carbon monoxide emission would reveal molecular gas masses, the fuel for future star formation. Resolving spatial structure would show whether star formation is centrally concentrated or distributed. Measuring stellar masses through modeling of spectral energy distributions would confirm whether these systems truly contain as much stellar mass as their brightness suggests. These additional measurements will refine the theoretical challenge. If follow-up observations reveal that bright, high redshift galaxies contain less stellar mass than their luminosity implies, perhaps due to unusual stellar populations or active galactic nucleus contamination, the discrepancy with models reduces. If follow-ups confirm substantial stellar masses and extended structures, the theoretical problem intensifies. Data quality and quantity continue improving, tightening constraints. The emerging picture shows an early universe more active and productive than expected. Galaxy formation did not proceed at a leisurely pace over billions of years. Instead, it kicked into high gear immediately when conditions allowed. The first few 100 million years saw explosive development. By the time 1 billion years had passed, much of the work of galaxy formation was already complete. The universe grew up fast. The rapid evolution pattern challenges comfortable assumptions about gradual hierarchical assembly. If small structures did not take billions of years to merge into larger ones, then either mergers happened much faster than thought, or large structures formed more directly without requiring extensive mergers, or the definition of what constitutes a galaxy in the early universe differs from modern usage. Rethinking galaxy formation from first principles may be necessary. Dark matter determines when and where galaxies form. This invisible substance outweighs normal matter by factors of 5. Its gravity pulls gas into dense concentrations where star formation occurs. Understanding dark matter's properties and distribution at early times is essential for explaining observed galaxies. Current observations suggest something unexpected about how dark matter behaved in the infant universe. The standard cold dark matter model assumes dark matter particles are massive, slow-moving, and collisionless. They interact only through gravity. This simplicity allows precise predictions for structure formation. Density fluctuations grow through gravitational instability in a well-understood manner. Small halos form first when fluctuations reach sufficient amplitude. Larger halos assemble later through mergers. The timeline depends on fluctuation amplitudes measured in the cosmic microwave background. Extrapolating forward from cosmic microwave background measurements, models predict that dark matter halos, massive enough to host bright galaxies, should be extremely rare at redshift 14. The probability of finding even one such halo in a survey covering the area observed by James Webb is very small, yet multiple candidates have been found. Either the observations are systematically biased, or the models underpredict high redshift halo abundances. Modified dark matter properties offer potential solutions. If dark matter is warmer than assumed, consisting of lighter, faster-moving particles, then small-scale structure formation would be suppressed, while large-scale structure forms normally. This could affect the merger rate and assembly history. However, warm dark matter conflicts with observations of the smallest dark matter halos detected through gravitational lensing. Constraints are tight. Alternatively, if dark matter particles interact with each other through forces beyond gravity, the internal structure of halos changes. Self-interacting dark matter creates halos with more uniform density profiles rather than the cuspy profiles predicted for collisionless dark matter. This affects how baryons behave within halos, potentially changing gas cooling and star formation. The magnitude of self-interaction required to significantly affect early galaxy formation would need to be carefully chosen to avoid conflicting with observations of galaxy clusters. Another possibility involves primordial black holes as a component of dark matter. If some fraction of dark matter consists of black holes formed in the very early universe, they would seed galaxy formation differently than particle dark matter. Black holes can accrete surrounding gas, growing and creating feedback that affects star formation. A population of seed black holes might accelerate the formation of the first galaxies. However, constraints from gravitational wave observations and microlensing surveys limit how much dark matter can be in the form of primordial black holes. The standard cold dark matter model may simply need refinement rather than replacement. Perhaps the transfer function relating early fluctuations to late structure has uncertainties at small scales relevant for early dwarf galaxies. Perhaps the initial fluctuation spectrum has features not captured by simple power law approximations. Small modifications might reconcile observations with theory without abandoning the successful framework. Baryonic physics could also be responsible, rather than dark matter properties. If gas cooling and star formation were far more efficient at high redshift than currently modeled, then even standard dark matter halos could produce bright galaxies. The feedback prescriptions used in simulations, which regulate how supernovae and stellar radiation affect surrounding gas, may not correctly capture physics in the extreme environments of the early universe. Getting feedback right is notoriously difficult and remains a major uncertainty in galaxy formation models. Observations at slightly lower redshifts provide additional constraints. If early galaxy formation is due to modified dark matter, the effects should persist and be visible at redshift 5 to 10 as well. If the effects are specific to the highest redshifts, then environmental differences or evolutionary processes, unique to the earliest times, are more likely responsible than fundamental dark matter physics. Comparing galaxy populations across redshift helps isolate causes. Future observations will test dark matter scenarios directly. Gravitational lensing of distant galaxies by foreground dark matter halos allows measurement of halo masses and density profiles. Comparing lensing measurements at various redshifts constrains how dark matter halo properties evolve. Discrepancies between predicted and observed evolution would point to new physics. These tests require large samples and high-precision measurements, but are achievable with upcoming facilities. The abundance of satellite galaxies around larger systems also tests dark matter models. Cold dark matter predicts more small satellites than observed locally, the famous missing satellites problem. Perhaps many satellites exist but fail to form stars and remain dark, or perhaps dark matter physics prevents their formation. Observing satellite populations at high redshift before environmental effects stripped gas from small halos may resolve this long-standing tension. Dark matter governs the scaffolding upon which visible structure builds. Any unexpected behavior in that scaffolding creates visible consequences. The early galaxies now being discovered represent consequences we did not anticipate. Whether the cause lies in dark matter itself or in how baryons respond to dark matter remains uncertain. Disentangling these possibilities requires more data, better models, and creative thinking. The invisible foundation cracks under scrutiny. Galaxies assemble through complex processes involving gravity, gas dynamics, star formation, and feedback. Each process has characteristic timescales imposed by physics. Gravity acts quickly, collapsing structures in free fall times. Gas dynamics involves pressure, cooling, and turbulence that slow collapse. Star formation converts gas to stars over timescales of millions of years. Feedback from stars affects surrounding gas, regulating future formation. Coordinating all these processes should take time. The observed galaxies suggest coordination happened remarkably quickly. Consider the steps required. First, dark matter density fluctuations must grow to nonlinear amplitude where halos virialize. Virialization means the collapsing structure reaches dynamical equilibrium, with motions randomized and potential energy converted to kinetic energy. This sets the gravitational potential well within which gas can accumulate. Virialization timescales depend on the halo mass and initial overdensity. Second, baryonic gas must fall into the dark matter potential well. Gas starts at the mean cosmic density and must flow inward. This infall is hindered by pressure resistance. As gas compresses, it heats. The heated gas must radiate energy to continue collapsing. Radiative cooling proceeds through atomic transitions with rates depending on gas density, temperature, and composition. In the primordial universe with no metals, cooling via atomic hydrogen lines is relatively inefficient. Third, cooled gas must reach densities where star formation occurs. This requires gas clouds to become self-gravitating and unstable to further collapse. Turbulence, magnetic fields, and thermal pressure all resist collapse. The gene's mass sets the scale where gravity overcomes pressure. Only clouds exceeding the gene's mass can collapse to form stars. Building up sufficient gas mass in a concentrated region takes time as more gas continues to rain in from the surrounding halo. Fourth, star formation itself proceeds through complex physics involving fragmentation of molecular clouds, formation of protostellar cores, accretion onto protostars, and ignition of nuclear fusion. This sequence requires multiple timescales. The free-fall time gives the minimum duration for a cloud to collapse. Accretion timescales determine how quickly protostars gain mass. The Kelvin-Helmholtz time governs how long a protostar takes to contract to the main sequence. Summing these contributions yields timescales of hundreds of thousands to millions of years per stellar generation. Fifth, stellar feedback impacts the surrounding medium. Radiation from massive stars heats and ionizes nearby gas. Stellar winds blow material outward. Supernovae inject enormous energy, driving shock waves and potentially expelling gas entirely from the halo. The timescale for feedback to impact the system depends on how quickly supernovae occur and how far their energy propagates. In small halos, feedback acts quickly because scales are compact. The entire system can be affected within millions of years. Sixth, the cycle must repeat for multiple generations to build observed chemical enrichment. After the first generation of stars dies and disperses metals, the enriched gas must cool again and form new stars. Each cycle adds several million years to the total timeline. 3 to 10 cycles seem necessary to reach observed metallicity levels, implying total durations of tens to hundreds of millions of years. Remarkably, all these steps apparently completed within just 1 to 200 million years for for the galaxies observed at redshift 14. This suggests that processes overlapped in time rather than occurring strictly sequentially. Perhaps star formation began before all gas had finished falling into the halo. Perhaps multiple regions within a protogalaxy were at different evolutionary stages simultaneously. Perhaps feedback, rather than shutting down star formation entirely, sculpted gas flows in ways that sustained formation. Parallel processing across a spatially extended system could compress timelines. If a proto-galaxy spanning thousands of light-years contains multiple semi-independent star-forming regions, each region can evolve on its own timeline. When viewed as an integrated whole, the system appears more evolved than any single region because different regions contribute stars formed at different times. The overlap creates the illusion of rapid evolution when the actual pace per region is more reasonable. However, even accounting for spatial overlap, the timelines remain tight. The physics imposes lower limits that cannot be eliminated through clever accounting. Gas cooling cannot happen faster than radiative processes allow. Stars cannot evolve faster than nuclear fusion rates permit. Supernovae cannot disperse material faster than the ejector velocity. Each limit is firm. Making galaxy formation work within observed timescales requires pushing every process to near its physical limit simultaneously. This seems unlikely to happen by chance. More probably, some process or mechanism operating at early times does not appear in current models. Perhaps dark matter halos at high redshift accreted gas far more rapidly than predicted. Perhaps the radiation background from the first stars affected gas cooling in ways that enhanced rather than suppressed star formation. Perhaps magnetic fields, largely ignored in current simulations due to computational cost, played important roles in channeling gas and regulating collapse. Identifying missing physics is the next challenge. The universe accomplished in hundreds of millions of years what models say should require billions. The reionization of the universe marks a major phase transition. Neutral hydrogen dominating the early universe gradually became ionized by radiation from the first stars and galaxies. This process transformed the intergalactic medium from opaque to transparent over several 100 million years. The timing and nature of reionization remain incompletely understood. Early galaxies, like the discovered system, provide critical clues about this epoch. Reionization required enormous amounts of ionizing radiation. Every hydrogen atom in the universe needed to absorb an ultraviolet photon energetic enough to strip away its electron. This happens at wavelengths below 91 nanometers. Only hot stars produce sufficient ultraviolet flux in this range. The most massive stars, with surface temperatures exceeding 30,000 degrees, emit prolifically in the far ultraviolet. Early galaxies, dominated by massive stars, would have been prodigious ionizing sources. The observed galaxy's properties suggest it produced ultraviolet radiation efficiently. High star formation rates, inferred from emission lines, mean many massive stars forming continuously. These stars lived briefly and died as supernovae, but while alive, they blazed with ultraviolet light. A significant fraction of that light would have escaped the galaxy and ionized surrounding intergalactic gas. The escape fraction of ionizing radiation determines how effectively galaxies contribute to reionization. Measuring escape fractions directly at high redshift is challenging. Ionizing photons get absorbed by neutral hydrogen in the intergalactic medium before reaching our telescopes. We only detect light at longer wavelengths that is not absorbed. Indirect methods involve measuring non-ionizing ultraviolet flux and modeling stellar populations to estimate how much ionizing flux should be produced. These models depend on assumptions about stellar temperatures, atmospheres, and mass distributions. The chemical composition affects ionizing output. Metals in stellar atmospheres absorb some ultraviolet light before it escapes the star. Metal-poor stars emit more ionizing photons than metal-rich stars of the same mass. The relatively high metallicity of the observed galaxy suggests its stars contained enough metals to slightly suppress ionizing output compared to truly pristine population. 3 stars. However, the stellar population was likely still more metal-poor than typical modern stars, maintaining high ionizing efficiency. The galaxy's contribution to reionization depends on both its ionizing photon production rate and its number density. If similar galaxies were common at this epoch, collectively they could provide significant ionizing flux. If this galaxy represents a rare object, its individual contribution would be minor. Current estimates suggest that galaxies observed by James Webb at high redshift are numerous enough to have driven reionization, but uncertainties remain large. Reionization proceeded inhomogeneously. Dense regions containing more galaxies ionized first, creating ionized bubbles that expanded outward. Lower density voids between galaxies remained neutral longer. Eventually, the ionized bubbles overlapped, completing reionization. The topology of this process, the size distribution of ionized regions, and the timing of overlap all depend on the spatial distribution of early galaxies. Observations of distant quasars provide information about reionization's progress. Quasar light passing through the intergalactic medium shows absorption features from neutral hydrogen along the line of sight. The amount of absorption indicates the ionization state of the medium. Measurements show that the universe was substantially ionized by redshift 6, with reionization largely complete. Earlier than that, ionization fractions decrease, indicating reionization was ongoing. The discovered galaxy at redshift 14 existed during the early phases of reionization. The intergalactic medium around it contained a mixture of ionized and neutral regions. The galaxy itself sat within an ionized bubble created by its own radiation and that of neighboring galaxies. The size of this bubble depends on how long the galaxy had been producing ionizing photons and how quickly those photons propagated into surrounding neutral gas. Simulations of reionization attempt to track the growth and overlap of ionized bubbles. These simulations require knowing the galaxy population at each redshift, including their number density, spatial clustering, and ionizing output. Observations of real high redshift galaxies provide critical input for these simulations. Each new discovery refines the models. The cumulative effect of many observations will be a realistic simulation of how reionization unfolded. The relationship between galaxies and reionization is bidirectional. Galaxies caused reionization by producing ionizing radiation, but reionization also affected galaxies. Ionized gas has higher pressure than neutral gas, making it harder to collapse into low-mass halos. Reionization may have suppressed the formation of small galaxies, setting a minimum mass scale for galaxy formation. This photoevaporation process would be visible as a change in the galaxy mass function before and after reionization. Understanding reionization matters for interpreting observations at all cosmic epochs. The ionization state of the intergalactic medium affects transmission of light from distant objects. It influences the temperature and pressure of gas that eventually falls into galaxies. It determines the radiative environment in which early galaxies evolved. Reionization was a watershed moment in cosmic history, separating the dark ages from the age of galaxies. Pinpointing exactly when and how it happened remains a frontier question. Early galaxies hold the answers. The fog lifted through their light. Finding and characterizing this galaxy required extraordinary observational effort. Over 200 hours of James Webb Space Telescope time were dedicated to this small patch of sky. In an era when telescope time is among the most valuable resources in astronomy, this investment represents a major commitment. The return justified the cost. The observations occurred in multiple phases using different instruments. The near-infrared camera provided initial imaging across multiple wavelength bands. Each band required separate exposures to build up sufficient signal. Longer exposures reduce random noise, allowing fainter objects to be detected. For the deepest bands, integration times exceeded 30 hours per filter. The telescope stared at the same region for hours, slowly accumulating photons. Scheduling these observations required careful planning. James Webb orbits the second Lagrange point, 1,000,000 miles from Earth. Its field of view can only point at certain parts of the sky at certain times of year. The target region needed to be observable during the scheduled observation windows. Weather on Earth does not affect space telescopes, but instrumental scheduling, data storage limitations, and competing observation requests all constrain what can be done when. The mid-infrared instrument observations added another layer of complexity. MIRI requires even longer integration times than NIRCam due to lower sensitivity. Infrared backgrounds from the telescope's own thermal emission must be carefully subtracted. Observations alternated between on-source pointings and offset pointings to measure the background. This calibration consumed additional time beyond the pure science integration. Data reduction transformed raw detector frames into science-ready images. Each frame contains instrumental signatures that must be removed. Hot pixels, cosmic ray hits, electronic noise, and flat field variations all appear in raw data. Pipeline software corrects these effects using calibration files derived from laboratory and on-orbit characterizations. The process is automated, but requires human oversight to catch anomalies. Combining multiple exposures into final images requires precise alignment. Between exposures, the telescope pointing drifts slightly due to thermal variations and micro-vibrations. The images must be registered to sub-pixel accuracy before co-adding. Software identifies stars or other point sources that appear in multiple frames and calculates the offset between frames. After shifting frames to a common reference, they can be averaged, increasing signal-to-noise ratio. Spectroscopic follow-up demanded additional time. The NIRSpec instrument can observe dozens of objects simultaneously using a programmable micro-shutter array. Small metal shutters open or close to create custom slit patterns. Configuring the shutters for this galaxy required knowing its precise position from the images. The spectrum was built up through many individual exposures, each lasting thousands of seconds. Different gratings provided coverage at different wavelengths. ALMA observations from the ground complemented space-based observations. Arranging ALMA time is also highly competitive. Proposals are reviewed and ranked. Only the highest priority science receives time. The ALMA observations required excellent atmospheric conditions, achieved only a fraction of the time at the high-altitude site. When conditions were right, the array pointed at the target for hours, letting the Earth's rotation provide different baselines and build up coverage in the Fourier plane. Data from multiple telescopes and instruments had to be combined carefully. Each dataset has different calibration, uncertainties, and systematic effects. Merging them requires understanding these systematics and weighting data appropriately. When different measurements agree, confidence increases. When they disagree, troubleshooting is required to identify which measurement is problematic. The human effort behind the observations should not be overlooked. Dozens of astronomers contributed to planning, executing, reducing, and analyzing the data. Each brought specialized expertise. Some designed optimal observation strategies. Others developed data reduction algorithms. Still, others interpreted the scientific results. Collaboration across institutions and countries made the work possible. No single person could have accomplished this alone. Publishing the results required careful documentation. Scientific papers must describe methods in sufficient detail that other researchers can evaluate the conclusions. The supplementary materials for this discovery include hundreds of pages of technical details. Peer reviewers scrutinized every claim before publication. The process ensures quality but takes months to years from initial submission to final publication. The observational investment will pay dividends for years. The deep images and spectra can be reanalyzed to study other objects in the field. Fainter galaxies, previously below detection thresholds, might emerge from the noise with improved analysis techniques. Serendipitous discoveries often emerge from data taken for different purposes. The dataset is a resource for the entire astronomical community. 200 hours staring at darkness revealed light. This discovery is just the beginning. Finding one galaxy with extreme properties raises the question of whether others exist. Are such objects common or rare? Answering this requires observing many more fields to detect additional examples. Multiple future observations are planned to address this question. James Webb will continue surveying high redshift galaxies as part of its ongoing mission. The JADES program has multiple observation cycles approved, covering additional areas of sky to varying depths. Each new field provides opportunities to find similar objects. By observing many fields, astronomers build statistics on the abundance of bright, chemically evolved galaxies at various redshifts. Patterns emerge only with sufficient sample sizes. Other deep surveys using James Webb target different regions and use different strategies. Some focus on wider areas with shallower exposures, efficiently finding the brightest objects. Others drill extremely deep into small regions, pushing to the faintest possible limits. The combination of wide and deep surveys samples different populations. Wide surveys find typical objects. Deep surveys find rare objects. Both are necessary for complete understanding. Ground-based telescopes continue playing important roles. ALMA is conducting systematic surveys of high redshift galaxies to measure their molecular gas content. These observations complement the stellar population information from James Webb. Together, they constrain both the stars and the gas, providing a complete picture of galaxy properties. ALMA's large collecting area and excellent sensitivity make it ideal for spectroscopic surveys. Future extremely large telescopes will provide even better capabilities. The Giant Magellan Telescope, 30-meter telescope, and Extremely Large Telescope, all currently under construction, will be the largest optical telescopes ever built. Their mirror diameters exceed 25 meters, providing collecting area more than 10 times that of current large telescopes. This enables spectroscopy of fainter objects and higher resolution imaging to resolve internal structures. Space-based missions beyond James Webb are under development. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will conduct wide-field surveys covering areas 100 times larger than Webb can efficiently observe. Roman will find thousands of high redshift galaxies, identifying the most interesting targets for detailed follow-up with other facilities. Its panoramic view complements Webb's deep focus. Further in the future, mission concepts exist for telescopes even more powerful than James Webb. The Habitable Worlds Observatory aims to directly image and characterize Earth like planets around nearby stars, but will also have capabilities for studying distant galaxies. LUVOIR, the large ultraviolet optical infrared surveyor concept, would dwarf James Webb in size and sensitivity. These missions remain decades away from launch, but represent the long-term future of space astronomy. Radio astronomy continues advancing with new facilities. The Square Kilometre Array, under construction in Australia and South Africa, will be the most sensitive radio telescope ever built. Its large collecting area will enable detection of faint emission from high redshift galaxies, measuring their gas properties and kinematics. The NGVLA, Next Generation Very Large Array, proposed for construction in the United States, would provide similar capabilities with higher resolution. Coordinated multi-wavelength observations extract maximum science from each target. When a new high redshift galaxy is discovered in infrared images, follow-up observations at radio, submillimeter, and optical wavelengths build a complete dataset. Each wavelength probes different physical properties. Combining information across wavelengths constrains models far better than any single wavelength could. International collaborations ensure that appropriate facilities are applied to the most interesting targets. Machine learning techniques are being developed to identify high redshift galaxy candidates automatically in large datasets. Humans can visually inspect hundreds of images looking for red, faint objects. Computers can inspect millions. Training algorithms on known high redshift galaxies allows them to recognize similar objects in new data. Automated candidate selection accelerates the discovery process, though spectroscopic follow-up is still required to confirm redshifts. Citizen science projects engage the public in galaxy classification and discovery. Platforms like Galaxy Zoo allow volunteers to examine astronomical images and classify objects. Occasionally, volunteers discover unusual objects that professional astronomers missed. The collective effort of thousands of volunteers can process datasets too large for small research teams. This democratization of discovery benefits both science and education. Theoretical predictions guide where to look for interesting objects. Simulations of galaxy formation identify regions of parameter space where extreme objects might exist. If models predict that the brightest high redshift galaxies preferentially form in overdense regions, then surveys targeting known overdensities will be most efficient. Combining theory and observation optimizes telescope time usage. The sample size will grow over the coming decade. Dozens of similar objects may be found, eventually hundreds. At that point, the statistical characterization of early galaxy populations becomes robust. Individual objects transition from curiosities to representatives of a population. The questions shift from, "Does this exist?" to, "How common is this?" and "What causes the observed distribution of properties?" The field matures from discovery to understanding. The search expands across the sky. Chemistry enables complexity. Without heavy elements, no planets could form. Without oxygen, no water could exist. Without carbon, no organic molecules could emerge. The rapid chemical enrichment revealed by this galaxy has profound implications for when and where the building blocks of life first appeared in the universe. The story of chemistry is the story of possibility. In the primordial universe, only hydrogen, helium, and trace lithium existed. These three elements alone cannot build complex structures. No solid surfaces can form. No long-chain molecules can exist. No self-replicating systems can emerge. Life requires more diverse chemistry. That diversity comes from stellar nucleosynthesis, the fusion of light elements into heavy ones inside stars. Every carbon atom in your body, every oxygen molecule you breathe, every calcium atom in your bones was forged in a star billions of years ago. The timeline for chemical enrichment determines when the prerequisites for life could first be met. If enrichment takes billions of years, then the earliest epochs remain chemically hostile. If enrichment proceeds rapidly, then the potential for complex chemistry and eventually life arrives early. The discovered galaxy proves enrichment began almost immediately in cosmic terms. Within 300 million years, significant oxygen existed, probably carbon, nitrogen, and other bioessential elements existed as well. This does not mean life arose at redshift 14. The chemical preconditions are necessary, but not sufficient. Planets must form from enriched material. Those planets need stable environments, allowing liquid water. Organic chemistry must produce increasingly complex molecules. Self-replication must emerge. Each step requires additional conditions beyond mere element availability. The pathway from chemistry to biology is long and uncertain. However, the early appearance of heavy elements opens wider windows of opportunity. If galaxies at redshift 14 contain sufficient oxygen to form water and sufficient carbon to build organic molecules, then the clock for biological evolution could have started surprisingly early. In principle, Planets forming from gas enriched by these early galaxies might have had billions of years for life to develop before Earth even formed. Such ancient biospheres could exist on planets orbiting stars born in the first billion years of cosmic history. The distribution of elements matters as much as their total abundance. If early enrichment was highly localized, with oxygen concentrated in small regions while most of space remained pristine, then planet formation would succeed only in favored locations. If enrichment was widespread, then opportunities for chemistry existed broadly. The efficiency of mixing enriched ejecta through galaxies determines how uniformly heavy elements distribute. Supernovae in the early universe exploded into denser environments than later supernovae. The intergalactic medium was more compact. Ejecta from one supernova could travel less far before encountering significant amounts of gas. This favored efficient mixing on galactic scales, but might have limited enrichment of the broader intergalactic medium. Voids between galaxies probably remained more pristine, longer than regions within galaxies. The first generation of planets formed from slightly enriched material contained more heavy elements than population, 3 stars but far less than Earth. Such low metallicity planets would differ from modern rocky planets. They might contain relatively more carbon compared to oxygen, producing carbide minerals rather than silicates. Their atmospheres might be hydrogen-dominated, resembling small versions of gas giants. Whether such planets could harbor life remains speculative but intriguing. Finding planets around metal-poor stars provides tests of early planet formation theories. Recent surveys have detected a few planets orbiting stars with metallicities below 10% of typical values. These discoveries prove that planet formation can occur with limited heavy elements. The minimum metallicity for planet formation remains uncertain. Perhaps even first-generation stars with metallicities below 1% could form some planets. Each new discovery pushes the limit lower. The presence of water elsewhere in the universe depends on oxygen abundance. Water molecules require oxygen atoms to bond with hydrogen. The discovered galaxy's high oxygen content guarantees that water could have formed in or around it. Clouds of water vapor might have existed in the galaxy's interstellar medium. Icy planetesimals might have condensed in protoplanetary disks. The ingredients for water emerged surprisingly early. Life as we understand it requires liquid water, but many chemicals participate in biology. Amino acids, the building blocks of proteins, contain carbon, nitrogen, oxygen, and hydrogen. Nucleic acids, forming DNA and RNA, additionally require phosphorus. Lipids, forming cell membranes, consist of carbon and hydrogen chains. Each element becomes available through stellar nucleosynthesis at different rates. Achieving the full suite of bioessential elements requires extensive enrichment. The implications extend beyond life's possibility to its inevitability. If chemical enrichment proceeded rapidly everywhere, then the universe quickly became filled with the raw materials for complexity. Billions of galaxies, each containing billions of stars, each potentially hosting planets with the right chemistry. The sheer number of potential sites makes life elsewhere in the universe seem almost certain. The question shifts from, could life exist elsewhere, to, how common is it? And, where should we look? Searching for biosignatures in exoplanet atmospheres represents one approach to finding life beyond Earth. Upcoming telescopes will analyze the atmospheric composition of potentially habitable planets, detecting oxygen, methane, and other gases in combinations suggesting biological activity would provide evidence. However, false positives from non-biological processes remain possible. Confirming life requires multiple independent lines of evidence. The chemical history of the universe unfolds as a story of increasing complexity, from simple hydrogen and helium to the full periodic table, from primordial clouds to stars and planets, from minerals to molecules, from chemistry to biology, from simple organisms to intelligence. Each step builds on previous ones. The rapid chemical enrichment of the early universe accelerated this progression. The timeline from Big Bang to complex chemistry compressed into hundreds of millions of years instead of billions. The discovered galaxy represents a milestone in that progression. It marks the era when chemistry diversified, when possibilities expanded beyond simple hydrogen and helium. The oxygen in its spectrum signals the end of chemical simplicity and the beginning of elemental richness. That transition made everything that followed possible. Stars like our star, planets like our planet, life like our life. The chain of consequence connects that ancient galaxy to us. We are made of the ashes of those first stellar generations. Their explosions enriched the gas that eventually became our solar system. Their chemistry is our chemistry. The universe learned to make elements quickly. Then it had billions of years to explore what those elements could become.